Uh, Today we are going to learn about the ice plant tutor. Basically, this is a tutor which is used to teach the students about the working of the vapor compression cycle. Vapor compression cycle is used in all the domestic refrigerators, all the air conditioners and all the air conditioning and refrigeration devices, including the ice plant and cold storage and everywhere. Wherever you will find the uh, confinement being cooled or the articles are being cooled, the system which is used is the vapor compression cycle. So this is a very good setup to explain the concept of vapor compression cycle to the learners. Now we are doing this whole experiment into four parts. The first part will be all about the introduction and the flow of the refrigerant working substance, how the refrigerant flows from one part to another part, and what are the various. Second part will be the introduction about the various components, which are the compulsory components of the vapor compression cycle, and then we will also talk about the accessories which are kept over here in this cycle. So we'll learn about the accessories also. Third part will be starting the setup, and we'll be taking the various readings of the pressure and the temperatures. At every salient points, the pressure and the temperature tappings are there, which are used to measure the pressure and temperature, flow rate, and the other things are there which can be measured with the help of this setup. And finally, the fourth part of this experiment will be the plotting those readings onto the pressure enthalpy chart, that is the pH chart, and then we will be finding out the various values. So learning how to use the pH chart, that is the fourth part of this experiment here. So we start with the first part. So first of all, we have got the pictorial display of the compressor over here. We start with the compressor, and this is the pictorial display, and the actual compressor is on the back side of the setup. So we switch to the back side of the setup. This is a compressor basically, and this is a reciprocating compressor, and this is capped inside the hermetically sealed unit. This is a sealed unit. Look at this. This is a completely sealed unit. The hermetical word is used in order to tell you that the entry of the air inside this confinement is restricted. We have got, if I explain this hermetical word more to you people, then I'll give the example of the bulbs which you used to use after 5 years back, which used to have the filaments in it, and then when you used to switch on them, the filament used to glow and they used to give the light to us. So now those bulbs are hermetically sealed. Air entry is restricted, oxygen entry is restricted inside this. So this is also a hermetically sealed one. It has got the reciprocating compressor, which is mounted on the same shaft as that of the motor. Motor is also inside this only. Now this crankshaft, the crankshaft of the compressor is the shaft on which the motor is mounted. So this is the thing here. Now look at this black one. This black one is the inlet or the suction of this compressor, this insulated one, because this is a suction of the compressor, and this red one is the exit of the compressor. This is the exit of the compressor. These are the two pipes which are connected to the compressor, the suction and the exit. Now this green one is an extra pipe which is having a valve here and a perfect closure over here. This small tapping of this green pipe is used for charging the whole unit. The whole unit can be charged with the help of this by removing this and by opening this. It can be connected to the refrigerant, and this system can be charged with the help of this whole setup, which is closed one here. Usually it is a pinched off pipe. In this case here, it is not pinched off. It is closed by the wall and the a closing type of the cover, a closing cover here. Now this is the cutout, electrical cutout, so which is used for the safety device, as a safety device, and the condenser over here. So two electrical connections are there which are supplying the the current to the motor which is inside this here, and this is all about the compressor. Now we come to the second part, which is the condenser. Uh, I have shown you the exit of the compressor. So this is the exit of the compressor, which is pictorially depicted on this board. Now this exit of the compressor, you can see the tubing on the back side. This exit of the compressor is connected to this condenser. This is a condenser. The condenser is a heat exchanger basically. And in this case here, the setup makers have used directly a radiator of the automobile. They have used the radiator of the automobile, and they have put the radiator of the automobile as a condenser, because radiator is an excellent heat exchanger which is used to drop the temperature of the cooling water. Here this is a heat exchanger. Condenser is a heat exchanger which is used to cool down and drop down the temperature of the refrigerant, which is coming at high pressure and temperature from the compressor, and it goes to the condenser. The condenser cool it down, and then the cooled one, and we don't consider any pressure loss, though the travel of the refrigerant from this point to this point will lead to some pressure drop, but theoretically we are neglecting this pressure drop. We are considering the condensing process as a constant pressure process. Now from condenser, the refrigerant is going to the dryer. This is a dryer and the filter. At the back side, you can see this. You will see that dryer and the filter. This is a closed confinement. Usually silica gel is filled inside the dryer. So if there any moisture content inside is there with the refrigerant, then the silica gel will absorb the moisture, and it will make the refrigerant free of the moisture, and it will also sieve out, because it's a filter also. So if there is any dirt or grit particle, or if is there any impurity, so that will also be sieved out or removed from this the dryer and the filter. This is not an essential part. This is an accessory which is used here. This back side, you can see the actual one here. We'll see that later. And then from this condenser, it goes to the flow measuring device, and the name of this flow measurement device is rotameter, and this rotameter is measuring the flow of the refrigerant in liters per hour unit. Now the working principle of the rotameter is like there is a float inside that. We'll see that how it is working when I'll start the whole system. You will see that there is a small float here. You can see that this is a small float, the white one. The float is here. This float, when the refrigerant flows from the bottom to the upward side, this is the float, white one. Now this float lifts, and the lift of this float is proportionate to, we will start and we will show you the lift of this. This lift of the float is used as a measurement of the flow, because the flow will apply the force onto the float, and there will be gravity force on the on the opposite direction. So flow will remain stationary somewhere, and wherever the flow becomes stationary, we read it from the scale. There is a scale over here which is graduated in liters per hour. The unit is liters per hour. So in the liters per hour, we are able to find out the mass flow rate of the refrigerant through the whole system in the liters per hour. Now we can convert, because we are not using the liters per hour, we are using the kilogram force per second. So we have got the conversion system. We convert that into the kilogram force per second. We'll do that into calculation part here. Now from the rotameter, this is not an essential part, boys. This is used in order to make it a working experimental setup. So this is not a compulsory part of the whole thing. Then from the rotameter, it goes to the expansion device. The expansion device here, it is used as a capillary tube expansion. We'll go behind and we'll see that. This is the capillary tubes here, and they are connected over here with this rotameter, and then the outlet. This capillary is also connected over here, so they can sense the temperature over here, and then another outlet of the capillary is connected to this tube. This is the tube here, and this is going to the evaporator. This is yellow one. This yellow one is evaporator. I'll show you again from the front side. This outlet of the capillary is going to the this yellow one. This is an ice box. This is ice box, and basically it is an evaporator. So we will learn about that later when we go in the front of the machine. Right now, I like to speak out something about the capillary. Basically, expansion can be of two types here. We can have the expansion behind a piston or cylinder arrangement. We can have the expansion because of the by a cooling turbine, or we can have the expansion by passing the refrigerant through a closed confinement, maybe a small tube of diameter 1 to 2 mm, and the basically pressure drops when the high pressure refrigerant passes through such a small diameter tube, which you can see over here. When it passes through it, the pressure drops because it has to face the friction. So friction is causing the loss in the pressure head, and basically we are having the expansion because of the friction encountered by the refrigerant in the small opening of the capillary tubes. So capillary, this is theoretically considered throttling process. Throttling process for the ideal gases is the isoenthalpy process, but for real gases, this is not isoenthalpy. So, after throttling, all three possibilities are there. The temperature may rise, temperature may remain unchanged, or temperature may drop. So, this is what we have to find out the pressure range, that what should be the value of the inlet pressure and what should be the value of the outlet pressure for the capillary, so that we get the desired effect, that is the cooling effect, that is a drop in the temperature. So pressure is to be selected. For this purpose, the Joule-Thomson inversion curves are used. The Joule-Thomson inversion curves are there. These Joule-Thomson inversion curves are plotted between pressure and temperature, and they are having the bell shape inverted constant enthalpy lines. On the basis of the pressure range, we come to know whether the temperature will drop or rise or will remain unchanged. So in this case, our priority is to drop the temperature. So we select the pressure range in such a way that we get the drop in the temperature. Now, the expansion causes the drop in the temperature, because Joule-Thomson effect says that when you drift the parts apart from each other, you have to work against the intermolecular forces of attraction. So when you have to work against the intermolecular forces of attraction, the substance loses its own internal energy because you are drifting them apart from each other. So the loss in their own internal energy will be manifested as a drop in the temperature. So from the expansion device, which we have seen on the back side, the tubes are connected. I have shown you that this is the ice box here. Now I am showing you the ice box. I am opening this. It is opened like this. Now I will request this camera person to show this evaporator. Now in this ice box, there is this type of containers are there. These containers are used for storing the water, so the ice can be made out of that. We have got many such containers are there inside this, and they are surrounded by the brine solution. The brine solution is there inside this. Brine solution is there. You can see that is a solution, which is a brine solution. So that is a secondary refrigerant. There are tubes inside this. So tubes are having the chilled refrigerant inside them, and which is connected to the brine, which are cooling the brine solution. And brine solution is transferring the heat is removing the heat of the water, which is inside these ice trays here, and that is how the ice is formed here. So at the same time, there is a small thermostat also connected over here. So this thermostat is there, which is used to see that the temperature and the need of the temperature for this particular evaporator here. Now this is the brine is a secondary refrigerant. Brine is a secondary refrigerant. The primary refrigerant in this case here is the R22. R22 is a Freon 22, or you can call it Melon 1, 2, these are the commercial names. Basically, they all are chlorofluorohydrocarbons. They are the chemicals which are mixture, which are either monochloro dichloromethane or monochloro tetrachloromethane, or like that. Here they are the chlorofluoromethanes. Here they are used. Here they are having low evaporation temperature. At the atmospheric temperature, they are almost in the vapor state here. So now let us see the measuring instruments over here. Now you will have the four pressure and the two pressure, the pressure which is pressure gauge over here, which is giving the suction pressure of the compressor. This is the pressure gauge. It's a simple pressure gauge. This is having the two units. One red one is inside a scale which is in the psi, and the black one is in the kilogram force per centimeter square. And now both these units are not in use because we are using SI units, so they are not in use. Neither the kilogram force per centimeter square is used, nor the pounds per square inch is used. So we have to convert this reading into the bar unit or SI unit or pressure unit or Newton per meter unit, something like that here. Now this is the cutoff, the LP and SP pressure switch, low pressure and high pressure switch of the compressor. So which is giving the value of the low pressure, high pressure value inside the compressor. So if it is a safety device which is used to if the pressure exceeds beyond a safe limit, then it causes the initiation of the cutoff. Now this device is the pressure device again, pressure measuring device. This gives the pressure at the outlet of the compressor, So this is the outlet of the compressor here. So it is used to measure the pressure at the outlet of the compressor. So those two pressure devices are there which are measuring temperature. Now one thermometer is over here. We are having the basically this bimetallic thermometer. They find out the temperature on the basis of the Seebeck and Peltier effects. They are measuring the EMF, basically the hot junction and the red junction and the cold junction, and then this is used to the EMF which is generated because of the temperature difference is shown in is calibrated in terms of dislice form, and we measure the temperature in the digital form from this particular indicator. And there is a knob here. This knob has got various T1, T2, T3, T4 tappings, and we can rotate this knob and we get the T1, T2, T3, T4, whichever you want here. Now what are the T1? T1 is the temperature at the suction of the compressor. Similarly, T2 is the temperature at the outside of the outlet of the compressor. Then T3 is the temperature at the outlet of the condenser. T3 is the temperature at the outlet of the condenser. This is the same. This is the same here. At the outlet of the compressor and inlet of the condenser. Outlet of the compressor and inlet of the condenser is the same temperature. We don't consider any change in temperature. So T2 remains over here and here both places here. T2 is only the temperature over here. T3 is the after condensation process. The temperature is T3 here, and then this is the rotameter which gives us the value of the flow rate of the refrigerant through the whole system. That comes out, this reads in the liters per hour, but usually we are using the SI unit, so this liters per hour will be converted into kg per second. We will be converting it into kg per second. The expansion device, and then the temperature. Just after expansion, the temperature before entry at the inlet of the evaporator. Evaporator is inside this. The coils are there. Evaporator coils are inside this. I have shown the details on the interior of this whole ice box. I have shown you details of the this ice box to you. Now T4 is the temperature, which is in the temperature at the inlet of the evaporator, and T5 is the temperature at the inside of the brine. You can find out the temperature of the brine also, which is a secondary refrigerant here. So which is a T5 here. So this is the all measuring things which are. One more thing, we have got a power meter here. We have got a power meter here. This is a watt meter basically, which you have got like one which in your houses. This is the energy meter. It is power meter. It measures the reading in kilowatt hour. It gives the reading in kilowatt hour. So it is directly giving the reading how much power the compressor is eating out in running this whole unit. So we have got one, but we are not using this. We'll be finding out the work of compressor with the help of the pH chart. So that is the thing here. Now there is a stirrer here. There's a button for a stirrer. A stirrer is kept inside here, which is a sort of a stirring device, and which is there inside this, which will not be visible, which is used to stir the brine solution, so make it uniform, so uniform all over. Then this is the power switch mains. We can switch on by turning this to this on button. This is switched on, and when this is switched on, this red bulb glows, means the power is on. And then we switch on this. This means that the compressor is on. This is the on off button of the compressor. So these are all instrumentations. One more, the thermostat is there. We have got thermostat here, which is there to see the various settings for the evaporator, that how much temperature you want. So various settings, various tappings are there. About 5 tappings are there. 5 settings are there in the thermostat. When you go, when you rotate it like this, you make the temperature drop inside the condenser. So this rotation causes cooler condenser, cooler evaporator. So that is the setting of the thermostat here. Now we are starting this setup. So the steps before starting the setup is like we have to be careful that these all connections are properly done, and they're already done because this is a closed system. So this is a power system. I switch on the power system over here, and I rotate this and put it to the on. So the power is on. Now I'm putting the compressor on. So now you can see the noise of the compressor. Compressor is on here. This is working on the back side. You can feel the vibration, and at the same time, this is the air cooled condenser. This is the fan behind the condenser is also started. So this process is started, and then there is a stirrer button over here to stir inside this. So I start this stirrer also. So stirrer is also stirring inside this. So and you can see, boys, the this thing, the float has lifted in the, but a lot of bubbles are coming, so let we wait for stabilizing the whole system. So we allow this whole thing to run for some time, and then we will take the reading. Meanwhile, you can see the pressure tappings. The pressure tappings here. This is giving the suction pressure over here, and this is the outlet pressure of the compressor, and then 2 only pressure, and the temperature readings here. This is the temperature T1 value, which is 25.9 degrees centigrade. This is T1. The temperature of the refrigerant which is entering inside the compressor is 25.26 now. So this is changing because the system is running. T2 is coming out to be something like 40.7 something, 41, maybe like 40.5 at present. This is the present one. We'll make it run for some time. This is T3. T3 is the temperature after the condensation process, which is 30.0. And then we have a T4, which is the temperature after the expansion. It should be lesser. Look at this. This is coming to be minus 15.1. This is quite less here. And if you find out the T5, which is the temperature of the brine solution, which is dropping, and which is about 20, is continuously dropping. Maybe it's present 26, but after some time this will drop. So this is the all 5 temperature values. Now this is the watt meter reading. We will not be using this because we will be finding out the values of the work done by the compressor with the help of the pH chart. So we make it run for some time, maybe 5 minutes, and then we will take the reading. So first of all, we take the temperature pressure at the suction of the compressor, which is P1, and the gauge is showing 0. Actually, this is not 0. This is atmospheric pressure, because gauge pressure 0 means it is above atmosphere. So this is atmospheric pressure. So you can consider it as 1.01 bar, or this is the inlet pressure here. The outlet pressure of the compressor is about 10. This is unit is kilogram force per centimeter square. So I put this is as 10 kilogram force per centimeter square. Now, which can be converted into bar. The conversion unit is 1 kilogram force per centimeter square is equal to 0.98 bar. 0.98 bar. So you have to multiply it with this 0.98 with this 10, and you get about 9.8 bar. So this is about 9.8 bar. Roughly it is 10 bar only. Roughly. So that is the two pressures. One is the 1 bar pressure almost, and second is about 10 bar, maybe 9.8 bar here. So these are the two pressure which are there in the circuit. Now we come across the temperatures. So first of all, I'll be reading T1 temperature. T1 is the temperature at the inlet of the compressor. That is the inlet of the compressor. Just the refrigerant coming out of the evaporator coil, and then the temperature at the inlet of the compressor is T1. The refrigerant coming out of the evaporator coil, its temperature is T1. So T1 is 26.4 degrees centigrade. So this is the T1 here. Now T2, this is to be rotated, so you get T2. T2 is the temperature after the compression process. Look at this, is quite high, because when the refrigerant is worked with the compressor, the temperature and the pressure both rises. The pressure rises from 1 bar to 10 bar, and the temperature rises from 26.4 to 65.2. Degree centigrade. So this is the why this is high. This is high because you are working onto it. You are working onto. When you put the air in the cycle, your own bicycle, with the help of the pump, you touch the pump, you will find that the pump walls are hot. So basically, when you compress something, then you are doing work onto that substance. When you work on that substance, the temperature and pressure both increases. So this is very well established. By T2 is more than the slightly more. Now T3, we come on the T3 here. T3 is the temperature, which is temperature at the outlet of the condenser. Now condenser is cooling this thing. This 65.2 degree is being cooled by the condenser, and now it is converted to 31.6. Look at the condenser efficiency. It is almost dropping the temperature to the half. This T3 is this temperature. The temperature of the refrigerant coming out of the condenser is about 31.7. This is 31.7. This is the 31.7, and now so this thing, and I think one more reading is left out. We'll take later this one. Now we take T4 temperature. T4 is should be very less, I tell you, because this is the temperature after throttling. As soon as throttling is done, the temperature drops to a greater extent. So T4. Look at this. This is quite low. Look at this. This is minus 8.4. This is minus 8.4. Quite low. And T5 finally, the brine temperature is 25.5, something like that. 25.5. Whatever. So that is the all temperature values here. We will not read this power meter reading, because we will be finding out the work of compressor with the help of the equations and the pH chart here. Now one more reading is left out, which is the reading of this rotameter. This is a rotameter, and this is a flow measurement device. This is used to measure the flow rate of the refrigerant. Refrigerant is coming from the bottom side, and applying force on this float. This white is a float here, white thing is a float. Now, because of the velocity of the refrigerant, the floats which was resting earlier on the bottom lifts up because the refrigerant pushes it up, and it is also acted with the gravity force from the up to down. So it is resting at this place somewhere. So the bottom pointer of this is indicating about 10.2 liters per hour. It is about 10.2. Flow rate is 10.2 liters per hour. This is the unit here. Now this liters per hour has to be converted into the our SI unit. So 1 liter per hour is equal to 0.00021 kg per second for this working substance. So we have to multiply and accordingly convert this liters per hour unit into the kg per second. So that we do here, and then these are the all readings. We have completed the reading session here. Now we can stop and now we can switch to the third part, the calculation and the pH chart, all about how to plot these readings on the pressure enthalpy chart and how to find out the values and how to do the calculation of coefficient of performance, refrigeration effect and work of compressor. These things we'll be doing. The refrigeration effect will be in the tons of the refrigeration, coefficient of performance will be unitless, and the work of compressor will be in kilowatt. This is the pressure enthalpy chart for the R22 refrigerant. R22 means monochlorodiafluoromethane. This is the chemical name of this R22 refrigerant, and this is on the x-axis we have got enthalpy, which is in the kilojoule per kg unit, and on the y-axis we have got the pressure, which is in the bar here. Now this line is a saturation liquid line. This line is a dark line, you can see this is a saturation liquid line, and this is the saturation vapor line. In between these two lines, they join somewhere outside this, which is not useful, so it's like dropped out. So this is a portion of the this curve which is useful for us. A small portion is taken up here. So now this area of this saturation liquid line is a weight area. So everything here is in liquid phase. Everything here is in the liquid phase. When we go inside this zone, this is a two-phase zone. Here the working substance is a mixture of liquid and vapor. Outside this zone, beyond this saturation vapor line, this whole zone is a superheated zone. Here the refrigerant is in the superheated condition. The horizontal lines are constant pressure lines, and the vertical lines as usual are constant enthalpy lines. So with the help of this chart, if we are able to know if we are able to plot the cycle on this chart, we can find out the enthalpies at various points. Enthalpies can be plotted at various points, and with the help of the enthalpy, we can find out the work of the compressor, the evaporation effect, and the consequently tonnage of the refrigeration ice plant tutor, and the work of the coefficient of performance. These all can be plotted if we know the properties with the help of this here. Now we start plotting the properties readings onto this chart here. We need a scale and the pen or maybe pencil. So basically the inlet pressure I was telling that is 1.01 bar. So we make it 1 bar here. The suction pressure is 1 bar. There is a temp pressure of the evaporator. So this 1 bar is here. 1 bar is here. So we drop a straight line from From 1 bar pressure, we drop a straight line. This is a straight line which we are dropping here. Now, we have to stop this. This line has to be stopped here. This line, this temperature, this is saturation vapor temperature at 1 bar, which from the table, we see the table at 1 bar, the saturation temperature is minus 40 degrees centigrade. So the temperature is minus, the saturation temperature is minus 40 degrees centigrade at 1.05 bar, that is almost 1 bar. So this temperature which we get from the reading is 26.4, which is not, so this is not the saturation point. This is the temperature we are getting is 26.4, which is more than the minus 40 degrees centigrade. So we have certainly in the superheat zone. Certainly in the superheat zone. So we have to see that where is the 26 degree. This is 25 degree, and one degree from 1 degree more from this 25 degree line. These are the constant entropy lines here. So 1 degree more. So maybe this is, you can consider this as a, this is 25 degree line. 25 degree line. So this you can consider this as a 25 degree line, and this intersection of this line, pressure line, and the 25 degree centigrade, maybe 26 degree, 1 degree more. And this is the first point number 1. So this we call as point number 1. At this point, the refrigerant enters the compressor. The compression process, we assume that it is a constant entropy process. So the line, these are the lines which are the constant entropy lines. They are, we chase it and we stop at 10 bar, almost 10 bar. This is the 10 bar pressure, 10 bar. This is the 10 bar pressure. So this line of the 10 bar intersecting, this is the line of 10 bar, this is intersecting with this constant entropy line. We are considering the compression process as asymptotic process. So this is the point number 2 which we get over here. This is the point number 2. So this is the position of the refrigerant after the process of compression. Now we are subjecting this to the condensation process. So condensation is again a constant pressure process. So this follows a constant pressure line, and we don't stop it here. We stop it because this temperature is 25 degrees centigrade, but after the condensation, temperature at the outlet of the condenser was 31.7. It is more than the 20 degree. So we are stopping somewhere 31. So this is a 31 line, 30 line, or maybe 1 degree more than this. So this is a 31. This is 0.3. So this is a two-phase mixture. After condensation, we are in the two-phase zone. In the two-phase zone, we are not in the pure liquid zone. We are in the two-phase zone. Some portion of the refrigerant has become liquid and some portion is still in the vapor position. So this is the point number 3 here, which is shown over here. Now the next process is the process of throttling. Process of throttling is isoenthalpy process. So we put a straight line from this with the help of the scale, which is going to meet the 1 bar pressure line. So at this point, this is meeting the 1 bar pressure line. So this is your point number 4. This is your point number 4. So this is the point at the entrance of the evaporator 4. This is the point at the entrance of the compressor 1. This is the point at the exit of the compressor. This is the point at the exit of the condenser, and again we are back onto the point which is the entry of the entrance point to the evaporator. You can put the arrow here, arrow you can put if you wish, you can put the arrow here, arrow you can put if you wish, you can put the arrow. If you don't want to put the arrow, it's okay, don't mind. This is how the whole cycle is traced onto the, this is the whole cycle which we can show on the piece of the paper over here. Let us see, these are the points here. Point 1 is coming somewhere here, point 2 is coming somewhere here, point 3 is coming somewhere here, and point 4 is coming over here. So this is the whole cycle which is plotted onto the pH chart, and now we can read the values of the enthalpy by the chart. So H1 is the enthalpy at point 1, which can be read from here. And I'm reading this H1. This is the H1 value. This is H1 value, which is about 395. H1 value has come. H1 value I'm putting from the chart. H1 value is coming 395 kilojoule per kg. Now H2 value I would like to find out. H2 value with the help of this scale, you can read from here. This is almost like 460 kilojoule. H2 is the value, which is 460 kilojoule per kg. Now S3 value you can very easily read from this graph here. This is the S3. This is almost 245. S3 is 245 kilojoule per kg. And finally the H4, which is to be read from S3 and H4 are same because the straight line. S3 and H4 are same because the straight line. Isoenthalpy process. So this is also same isoenthalpy process. So S3 and H4 are same. Then H1, all the values we are knowing now. So the H1 point, we read the value of the enthalpy on the H1 point, and this from this chart, and this comes out to be about 395 kilojoule per kg. Then S2 point, we read the enthalpy from the chart, and this comes out to be about 460 kilojoule per kg. Then S3 point we have plotted here, and we read the enthalpy. S3 and H4 will be same obviously, and we read this enthalpy from here, which comes out to be 245 kilojoule per kg. So these are the four key enthalpies which will be needed in the future calculations, and we have read from this chart after locating the all points by considering the superheat effect over here and the undercooling effect here, and all those effects we have considered. 2 points we have taken. We have considered the compression as the asymptotic compression, and we have considered the throttling process as isoenthalpy. So two assumptions are taken up in this calculation. With these two assumptions we do it. This is a quicker method to do it. In the practical life, usually we are not using the temperature entropy analysis. In the practical life, these pH charts and ready recognize the tables. They are highly recommended, and they do it in the short period of time. So the requirement is the use of the charts and the data because they consume less time. So it's a skill, and now they are available online also. So you can you very well find it out easily with the help of the available data here. So these are the values of the enthalpy over here. Now mass flow rate, which we have calculated out from the setup, was 10.2 liters per hour. Now this liters per hour is converted into kg per second by multiplying this multiplication factor, which is 0.00021 kg per second is equal to 1 liter per hour. So we convert this liter per hour into kg per second, which is 0.002 kg per second. That is almost 2 grams per second flow of the refrigerant is there. With the help of all this input, we find it out the work of compression. The work of compression is equal to mass flow rate multiplied by H1 minus H2. Sorry, this will be H2 minus H1 because H2 is the enthalpy after the compression and H1 is the enthalpy before the compression. So it will be S2 minus H1. This will be the correct one. So S2 minus H1 multiplied by mass flow rate, which is this thing here. So when you do this, this comes out to be 0.13 kilowatt. So for this reading, the work the compressor is incurring to drop the temperature is 0.13 kilowatt only. So this much is the work of compressor, which is one of our output, one of our requirement of the practical. The second is the refrigeration effect, which we are calculating out with the help of the H4 minus H1. So H4 is this value and this is the H1 here. So again it should be H1 minus H4, I'm sorry again. This should be H1 minus H4 here. H1 is this value and H4 is this value. So H1 minus H4, it will be H1 minus H4 here, refrigeration effect, which comes out to be about 150 kilojoule per kg. Now this has to be multiplied by the mass flow rate, which is 0.002 kg per second. So this has to be multiplied with this, and what you get, the refrigeration effect, is 0.3 kilowatt. So the capacity of this plant is 0.3 kilowatt. Now this can be converted into tonnage also. How much ton capacity is so much tons of refrigeration effect. So we know that 1 ton is equal to 3.5 kilowatt. 3.5 kilowatt is equal to 1 ton. So 0.3 kilowatt will be equal to 0.08 ton capacity. So the plant capacity comes out to be at ice plant Tutor capacity is very small at present here, 0.08 tons at present here. This is the capacity of the plant here. Now COP, the third point. So we have come out with the 2 points here. The last point, which is the COP. Now COP is defined as the refrigeration effect divided by the work of compression. How we get this? This we get as the ratio of the output upon input. The output is the refrigeration effect, the thanda hum kar rahe hain. The cool we are producing at present, that is the output here. Input is we are incurring the input in the form of the work of compression. The compressor is working, so that basically work of compression. So when we put these values, the refrigeration effect is 0.3 kilowatt, the work of compression is 0.13 kilowatt, the COP comes out to be about 2.3. So this is the final reading, final calculation. So we have come out with the refrigeration effect, we have come out with the work of compression, and we have come out with the COP of the unit. So all the three units we have taken, all the three things we have done. We have conducted a trial onto the ice plant Tutor, and we have calculated out, we have learnt about the working of the ice plant Tutor, we have learnt about the various components of which are the essential and not so essential features of the ice plant Tutor. We have discussed in detail all the components, their uses, and then we have talked about the various instrumentations which are used to find out the various readings and the values of this plant here. And finally we have started the setup, then we have taken the readings of the setup, and we have done the calculation, and the final set we have done, I have taught you how to locate the points onto the pH chart, how to use the pressure enthalpy chart for the R22 refrigerant here, which was also one of our aim of experiment here. So we have completed all the 4 aims of the experiment. That is how we finished this experimental work here. In the last, I would like to ask few questions of tutorial from you people. From your previous knowledge, you can answer that. So my first question is that how we define the 1 ton of refrigeration effect? What is the definition of the 1 ton of refrigeration effect? My second question is that why we need to go for the condensation of the refrigerant when it comes out of the compressor? Why don't we directly send it for the expansion? My third question is that what is the role of the capillary expansion device and how it works? My fourth question is that what is the Joule-Thomson effect and how it is used to find out the various pressure ranges for the refrigeration systems. And my final question is about the secondary refrigerant. What is the brine secondary refrigerant? What is the function of the secondary refrigerant, which is brine in this case here? Why it is used and what is the purpose of it? Thank you very much.